Welcome back all of you. In the last class we discussed a lot about relaxation. In fact, last couple of talks I would say we discussed a lot about relaxation phenomenon. We understood what is spin lattice relaxation, we understood what is spin relaxation, and we knew that spin lattice relaxation is the exchange of energy or transfer of energy from spins to the lattice. Spin interaction is an exchange phenomena between two spins, and it is the decoherence in the xy plane, where and also we understood the spin lattice relaxation is the growth along z axis, the magnetization growth. Spin relaxation is decay in the xy plane. For all these things to happen, there are various phenomena, and there must be some local fields generated at the site of the nucleus. This local field comes because of various motions. It could be diffusion, or it could be chaotic motion, tumbling motion, like that. And this motional frequency we can express in terms of spectral density function, and that must be at the lower frequency. Only then we can see that the spins gives energy to the lattice. Of course, same thing for the spin relaxation also we discussed, there must be local field. And then it also depends upon the correlation time, the JW depends upon the correlation time, we discussed that, and correlation time in turn depends upon the size of the molecule. And about what is the correlation time we discussed, it is the rotation of the molecule by 1 radian per second. So, that we also understood what is a correlation time, and it is generally of the order of nanosecond. We worked out some conditions like omega naught resonating frequency rate tau c. If it is very much greater than 1, what happens? If it is equal to 1 is the intermediate case, and it is very much less than 1, what happens? And how does the spectral density function varies, we saw. All those things we understood quite a bit. Finally, the conclusion was the relaxation is a radiationless transition. It does not create any rotation, or it does not create any magnetization in the xy plane for detection. The transitions from the spins from upper state to lower state, or from the lattice going from lower to higher, all things are happening, the transitions are there, but they are radiationless transitions. So, all these things we understood quite a bit. And as for the spin lattice relaxation is concerned, there are various mechanisms which aids for the spins to give energy to the lattice, like dipole interaction, chemical shift anisotropy, spin rotation, and quadrupolar relaxation, various phenomena we saw. And we also understood when there is a quadrupolar relaxation, sometimes it so happens lines will get even terribly broadened also, because of the resident time of the spins in the upper state or excited state is very small time. It relaxes very fast. The spreading the energy level is there. That is because of Heisenberg uncertainty principle, which we discussed in the earlier class or even in the previous course also. Those who have attended, fine, you would have understood that. So, but nevertheless, in some examples where the quadrupole coupling constant is much smaller, quadrupole moment is much smaller in some nuclei like deuterium or NH4, we saw the example, or BF4, where there is charge distribution is more like spherical, then it so happens we could see the coupling of heteronuclei with coupling of quadrupolar spin with the spin of nuclei, like CDCl3 we got the 3 lines of equal intensity for the carbon 13 because of the coupling with deuterium with spin 1. Same thing we saw for BF4 and also for NH4, we saw those things. So, that's we understood lot about various phenomena and everything about concept of relaxation. Is very fairly a tough topic. We tried our best to understand, and I tried to make it as simple as possible so that the concept should be understood clearly. But fine, we also understood after that we wanted to know how to measure the relaxation time, that is important. Now, we came to the measurement of spin lattice relaxation time. There are several methods I mentioned. Spin that can be measured by what is called inversion recovery, progressive saturation recovery, varieties of methods are there, and null method like that. But then most popular method in solution state is inversion recovery method. That is what we started discussing. So, now we will come back to the inversion recovery method today. I already showed this pulse sequence actually last week, in the last class. It is a simple 2 pulse sequence. Start with a 180-degree pulse and then give a delayed tau, and then apply a 90-degree pulse. Afterwards start collecting the signal. And before that before you apply 180 pulse, ensure that the spins attain thermal equilibrium. There is an enormous relaxation delay should be given, so that there should be thermal equilibrium for this magnetization in this place. And then you apply 180 pulse, what is going to happen? We already know what happens to 180 pulse. The magnetization will be tilted from z axis to minus z axis. That is fine. From here it will come to minus z axis. But then with the delay, it will start going back to z axis. Now you vary this delay, then it takes some time for the magnetization to go back to z axis. As a function of different time delay, we want to measure the signal. For the detection of the signal, we apply another pulse, 90-degree pulse after the tau delay, and collect the signal and start doing the Fourier transformation and measure the signal intensity. This is the simplest experiment that one can do for the inversion recovery, that is commonly practiced. So, signal intensity is measured as a function of the delay between the pulses used to obtain the value of T1. Okay. Now, what does 180 pulse does? As I told you, it inverts the spins, and magnetization is always along longitudinal axis, along z axis, and there is no transverse magnetization and no signal when when 180 pulse inverts this, and this is the largest deviation from the equilibrium population distribution that can be achieved by RF pulse. Anything less than that is only like 90 pulse etc., there will be magnetization in the transverse plane. The deviation from the equilibrium is not much. The deviation from the equilibrium is maximum within 180 pulse. This is the information which I wanted to tell you. So, now what will happen? The spins recover towards equilibrium position by losing their energy. This is what we wanted to know, how it loses the energy. We also discussed. Let us see diagrammatically what is happening. Let us look at magnetization after an 180 degree pulse. I told you 180 degree pulse inverts the spin populations. Now, consider a situation like this. I have alpha state and beta state. There are more spins in the alpha state than beta state. Some number we had chosen. It is not, you do not have to worry about the accuracy of this number. Just for calculation purpose, I will say, because the n is the total number of spin populations, I divide by n plus n by 2 here and add some number which is more, and here that much number is less here, that is all. So, there is a population difference between alpha and beta states. This is before 180 pulse. Now, we will apply 180 pulse. When I apply 180 pulse, what is going to happen? There is inverse, population gets inverse. See, beta state is here, alpha state is here. Now, n plus delta comes here and n minus delta comes here. Population gets inverted. This is an interesting thing is going to happen. So, population between gets inverted, and there is excess of spin population in the upper energy state now. This is quite unusual, because normally we know the population will be excess in the lower energy state. Now, because this is alpha 180 degree pulse, alpha and beta spin state population got interchanged. Now, we have more spins, excess spins in the upper energy state or in the beta state. That is the situation. Now, we have to understand what is population difference. Population difference delta P. I already told you population difference is always obtained from population difference from lower energy state to higher energy state. In this case, for example, if you want to consider what is the population difference in this case, you will see that in this case population difference is n plus n by 2 plus delta minus of n by 2 minus delta. So, this gets cancelled, this gets cancelled out, then it will become 2 delta. So, delta P is 2 delta after the 180 pulse. That is the thing which you should know. After 180 pulse, then delta P is be 2 delta. Before 180 pulse, this we are talking before 180 pulse. Now, when after a 90 degree pulse, what happens? Delta P equal to 0, exactly, because remember, applying a 190 degree pulse is as good as saturating the spin states. You are equalizing the population between two energy states. So, it is delta P is equal to 0, but 180 pulse makes this delta P equal to minus 2 delta. This is what we have to understand. Now, after the pulse, there is a slight excess spins, and these excess spins in the beta state cannot stay in the excited state for a long time. It has to come down. The spins which are in the excited state start dropping down slowly, like balls falling down from the upper state. It starts falling down. This is called spin drop. Spin drops from beta to alpha state. and remember, it does not create any rotation, it does not create precession, it does not create any magnetization. From beta state to alpha state, spin simply stops dropping down. That is what is going to happen. At time now half of t, t half let us say, which is equal to 0.693 of tau, then you can see that from the equation mz equal to m naught into 1 minus e to the power of minus t by t1, the population will become equal and mz equal to 0. That is the situation, that is a null point. At exactly half of this period tau t, then 0.693 of this thing if you take, the population become equal of the two states and it is mz equal to 0. Now, but from higher energy state, spin started coming down. After some time, both population difference became 0, but that is not enough. It has to come to thermal equilibrium. In the thermal equilibrium, there was excess population in the alpha state. So, it continues to drop further until alpha state gets more populated and excess population again becomes 2 delta. That is what I said in the previous slide. Before 180 pulse, it is delta p is equal to 2 delta and then 0, and after 180 I said minus 2 delta. Now, for minus 2 delta it has to come back to plus 2 delta. It goes through 0 and then come back to 2 delta and it comes to original state of thermal equilibrium, where the spin population will be excess in the alpha state and difference in the spin population is now again plus 2 delta. That is what happens. And you can work out simple mathematics. Delta mz at t is equal to 0 is equal to mz at t equal to 0, which is minus of m0. Okay. That is a simple equation, you know that at mz equal to t is equal to 0, difference between population at magnetization difference at t equal to 0 is magnetization t equal to 0 minus m0 equilibrium population. This mz at t equal to 0 is nothing but m naught. You substitute, it will become minus 2m0. Okay. Now, continue further. Delta mz at t is equal to mz of t minus m naught. That is what I said. Now, delta mz, this is already from the previous equation we know, which is equal to at t is equal to 0 e to the power of minus t by t1. Rearrange this equation little bit. Now, mz of t minus m naught, it will become minus of 2 m0 e to the power minus t t1, because we know what is the mz of t here. You can substitute that, it is minus 2 m0. So, it will become minus 2 m0 e to the power of minus t by t1. All I did is simple substitution, little arithmetic from our previous knowledge which we discussed here. So, what if you do, if you rearrange this term, now mzt becomes m naught, you bring it this side and take the m naught as a common factor outside, it will equal to m naught into 1 minus e to the power of minus 2 into e to the power of minus t by t1. This is the equation which we have been discussing, and we of course 2 was not there earlier. In the just for the relaxation, spin lattice relaxation, I said without 2 mz equal to m naught into 1 minus e to the power of minus t by t1 I said. Now, the 2 has come because of this experimental method which we are adopting, 180 tau 90 sequence for inversion recovery. So, this is the common equation you should see for this thing for inversion recovery, mz equal to m naught into 1 minus 2 to the power of e to the power minus t by t1. This is the important equation you remember. So, what we do is mz starts at minus m naught and at 0.693 t1 becomes 0 halfway through that equilibrium, and after a long time it will become m0. That is the process. So, mz going from minus z to z, plus z is only by dropping of the spins. I told you it is not a rotation, it is not precision, and there is no magnetization created because of this relaxation. As I have been telling you, it is a radiationless transition. There is no magnetization created, you cannot detect any signal, it is only a spin drop phenomena which is going on. From minus z to plus z it goes by dropping the spins which goes through 0. So, the magnetization vector, what happens? Initially it will be very large along minus z axis. See, let us say you apply a 180 pulse, bring the magnetization to this thing and then apply a 90 pulse. And when it brings to magnetization to minus z axis, it starts going back. Slowly then let us say minus z axis, this is the magnetization vector. Next, after when you reduce the time delay, let us say increase little bit less, little bit less, little bit less, it starts growing and then go through 0 and then start going positive. This is what happens. So, magnetization vector, the size of the magnetization vector keeps shrinking from minus z, reaches 0 magnitude and then start going towards the positive z axis. Up to what? Till it attains thermal equilibrium, this is going on. This is the important thing which happens. We will see that later, and this is experimentally what is being done, and this is what we are seeing. Now, with the 180 pulse I have brought back the magnetization to minus z axis. From plus z I have applied 180 pulse here already. Give some delay. Now, with that some delay, magnetization length reduced, it started shrinking, and then what you do, apply 90 pulse, collect the signal, and magnetization still not reached xy plane, it is still in the negative side, negative z axis, slowly it is coming up. So, intensity is negative like this, and keep on increasing the tau delay. Now, you have given enough time for the spins to come back to z axis. It does not fully come back, but slowly coming. Now, the intensity reduced here. Now, collect the signal. Now, this intensity reduced. Now, it went towards a positive and signal became positive, and after some time enormous tau value I have given, sufficiently long delay between 180 pulse and 90 pulse. Then what happens? The magnetization is completely recovered to what it was along the z axis before the application of 180 pulse. This is the phenomena what is happening. Magnetization initially will bring it to minus z, it starts shrinking as a function of time slowly and then go back to z axis. This is happening because of spin dropping of the spins, and it does not create any rotation. I am sorry, this is what it is. This is what you understand. Magnetization is less here, less here, less here. Whatever I showed in the diagrammatic in the stick plot, exactly if you plot it goes like this. Starts from negative, slowly start going and finally reaches the maximum, in that case thermal equilibrium. Beyond that it will not increase, there is a limit, and this should become equal to this, then it has come back to thermal equilibrium. But there is a point here, at this point it is tau half, that is the null point. That is the point I told you, a 0.693 times T1, you will get the T1 value also. So, the inversion recovery experiment is performed for different values of tau or T delay between the 180 and 90 pulse. The delay you have to keep on varying. Every time when you vary, you may apply 90 pulse, collect the signal, measure the intensity of the signal. Intensity of any one of the peak or all the peaks which you are interested to get T1 values, and make a plot of tau values as a function of intensity of the signal, and then do the curve fitting of that for the equation which is provided for T1 values. What is the equation? mz equal to m naught into 1 minus 2 into e to the power of minus t by T1. You have to do the curve fitting, fit this intensity values what you get for different tau values to this equation, and what mz equal to 0, you get a null signal, no problem. Do the fitting for all the intensity values you get, that is mz for different t values. And when you do curve fitting for each signal, whatever may be the number of how many peaks are there in the sample does not matter, for each individual peaks you get the corresponding T1 values just by doing curve fitting of this. Okay. This is an example to show inversion recovery of a molecule alpha P9. You see that now for 3.3 is a peak which is coming here, 3.2 is this proton, and see now what is happening as a function of this one, as a delay is kept on varying from 5 millisecond, 1 second, and finally you got up to 20 seconds. That is a large value. Initially 5 millisecond, 5 millisecond you use between 180 and 90, then all the signals are negative, inverted, and then starts growing backwards. Spin dropping has started, the signal has started growing towards the axis, and after sufficiently long time it has reached its original value. This is what the experiment looks like. You have to have how many number of points you have to take, depends upon how accurate you want the values. You can, depending upon the time available for you, you can take as many points as you like. So, this is what is happening for another molecule like toluene. For 3 different protons are there, aromatic proton, CH3 proton, and of course, this is for TMS reference. Okay. So, quick estimation, like you can do this experiment. It is a time consuming experiment. You have to give 5 times the delay between each acquisition. Remember, you have to make sure that relay is sufficiently longer so the spins come back to thermal equilibrium. So, it is very really time consuming experiment we have to do for lot of tau values and do the curve fitting. Now, you may ask me a question, is there any way I can quickly estimate the T1 value? Is it possible? Of course, it is possible. Simply look at this equation, mz equal to m naught into 1 minus 2 into e to the power of minus t by T1. This is the equation. Now, mz equal to 0 you put it, then rearrange the term, then tau null when it is 0, this will become T1 into ln of 2. You have to do the simple natural logarithm value of this, which you know, that is ln of 2 is 1.443. So, T1 value you can get it in nothing but the delay that you use for get the null signal, nullify the signal divided by ln of 2, which is ln of 2 is 1.443. So, then you can find out what is T1 value, very easy. So, it is a rough estimate, of course fairly accurate. So, if you want to get more precise values, you can do the curve fitting and get the accurate value, but it is a rough estimate, quick estimate of T1 value for any peak. If you go through the point at which magnetization is 0 in the inversion recovery, the null point gives you quick estimate of the T1. Okay, this is what it is for the different molecule at T1 inversion recovery. You can get and different spins in the sample. If you have different this thing, you can find out what is the T1 value for this proton, this proton, this proton, this proton. Each proton individually you can calculate by this thing. Okay, and as you can see, different protons can have a different. Look at this one. This is already recovered, but this has not. So, different peaks, different spins in the sample may have a different T1 values. You can use that to measure it. Okay, there is no point in going further. Now, there can be this is the null point which I wanted to say. For example, this one, you can get the precise value there. Okay, now I was telling you something about relaxing agents to help these spins relax faster. Let us say in this system we have many protons which have a very very long relaxation. If I have to do the inversion recovery experiment, it will take lot of time for me, especially if you look at the carbon 13, they have more relaxation time is much longer than protons. So, there are certain paramagnetic relaxation agents. I told you one of them is a Krakow. Krakow is a chromium acetyl acetate. If you add microgram quantity or very very small quantity of that, it helps in reducing the relaxation rate, and then as a consequence you can see you will get the signal much faster. Look at this one, this is much smaller. Look at this one. See, when the with the Krakow, the relaxations have become faster. It relaxes so fast. See, these two signals which were very weak in intensity here without Krakow has built up here with Krakow. This is where signal intensity keeps building up. So, this is what basically the rough idea I wanted to give you about how to measure the T1 with the inversion recovery sequence. When the T1 is very very large, you have certain other experiments like progressive saturation or saturation recovery. First saturate the signal and see how much time it takes to recover as a function of time, and then again do the curve fitting and may get the T1 value. There are various other experiments which I am not touching upon, because inversion recovery is the one which is very important. I discussed a lot. So, actually measurement of T2, we always use this, and now with T2 we have to do this thing, that is a different method now. T1 we understood. How do you do this T2 measurement? Actually T2 we have to measure. We discussed about the spin. We apply 90 instead of 180 90, it is tau 90 tau 180 we can use spin echo sequence. So, what is going to happen is, as we saw that as the echo starts decaying, if for a natural decay, natural T2 is T2, but we also say rarely we get the actual T2 value, because there are other contributions because of inhomogeneity of the magnetic field, etc. So, what you are going to measure is the T2 star. To get the actual T2, you have to remove the inhomogeneity contribution of the magnetic field. We know, we discuss all those things at stretch. So, we have to measure the T2, and then you have to ensure that the inhomogeneity contribution of the magnetic field is removed. So, what we use is a spin echo sequence. The spin echo sequence, as I told you, is first 90, then tau, 180, it could be x or y axis, does not matter. Give the identical delay here and then start collecting the signal and do the Fourier transformation. Very interesting thing happens. During this time, signal immediate 90 degree pulse decays according to T2 star, because inhomogeneity contribution is already present. And then after 180 pulse here, and after certain time exactly equal to this t, which is equal to tau, the spin start refacing. This is what is called spin echo. We discussed this in the previous course. I do not know whether in this course I did not discuss, but remember this echo sequences, echo is something very interesting. Apply a 90 pulse here, and then what happens, the spin start defacing different this thing. After applying 180 pulse, depending upon whether you apply along x axis or y axis, you can rotate the spins. You can make the spins flip for by 180 degree. Then what happens, the spins which are, let us say these are the fast moving components, these are slow moving components. If you start rotating this, inverting that, then again they start moving in the opposite direction and again refocus along particular axis. It can be in the same axis or on the y axis, depending upon where you are going to apply pulse x or y. Okay. So, spins exactly after the identical time given, it refaces and forms an echo. This is called spin echo, it forms an echo. Okay. So, echo amplitude, now what happens, start decaying as a function of time. This is what is going to happen. So, this is the echo amplitude, that echo amplitude start decaying, and that decay again you have to fit into the equation. What is that equation? It is bar minus t by t2, we discussed that. So, you have to do the curve fitting similar to what you be understood for T1 measurement. So, this is what is pictorially what is happening is shown here. See what happens is, as soon as you apply 90 degree pulse, the magnetization is brought to x axis, and then spin start defacing. Some spin goes in this direction, some goes in this direction, which we call as fast moving and slow moving components, and then give some time, the defacing keeps on going, and you give enormous amount of time, there is a complete defacing, there is no magnetization at all in the xy plane, there is a totally zero signal. Now see, now is there a maximum signal, I did not write here, signal intensity here comes down here like that. The vector addition of these components which are present here, if you take vector addition, the total magnetization start decreasing here, it starts shrinking here this. So, finally this it will become 0, but we will not go for that. Somewhere when they are defacing like this halfway through, what we do is we apply a pi pulse here. What does pi pulse do? Pi pulse will rotate this thing along this axis. In the x axis it undergoes, it makes the spins to rotate by 180 degree. Then what happens? These red spins which were moving like this will go like this, and then blue spins which are moving like this will come here, and then what is going to happen? They start moving in the opposite direction. You understand? The spins which are moving like this now start moving in the opposite direction, and you have inverted the spins in the x axis. Continue like that. Now they start coming backward. See, they were actually dispersing, going outside. Now they started coming backwards like this, slowly reduce, and finally after some time again they will come back to the same place where it started. It is a spin echo. It is like telling, make 10 people sitting in a row or standing in a row, ask them to run, visual. They keep on running. Different people have the different running speeds. Then after some time ask them to stop where they are, let them turn back, visual. Same amount of time if you give them, if they maintain the same speed, all of them will come back to the starting point. Exactly like that, similar analogy, the spins we started defacing will all come back and start refacing along the x axis to the same original state. This is what is going to happen, this is the spin echo. So, red spins which were higher field than blue spins precesses faster than the spins which, and they dephase also faster. 180 first started reversing, then they started going the opposite direction and then came back and became echo. So, only the tau delay, the spin echo reverses the effect of static inhomogeneity. If they are decaying, that you will find, but what is happening is there is inhomogeneity contribution that gets reversed, because the reversing effect gets reversed, inhomogeneity contribution will be removed. So, effectively effect of T2 star will be removed, you can measure actual T2 with this. And during the echo time there is some loss of phase because of natural transverse relaxation. Naturally spins are defacing, apart from inhomogeneity contribution which we remove by echo sequence. But in natural decay is not refocused. Inhomogeneity contribution is refocused, but natural decay is not. So, in effect then there is small loss of signal, there is a memory loss for the coherence with time, and this process has to be undone. So, this is what happens during echo, and they will try to come back and refocus, but during that process the intensity has reduced because there is a natural decay T2, and this is now devoid of contribution from the independent of field inhomogeneity. There is no inhomogeneity contribution. Take that and then start measuring the T2. You fit into the curve. But sometimes there will be pulse inhomogeneity. Pulse may not be 100, 180 pulse may not be exactly 180. It may be 178, 179 or 181 like that. But there could be similarly 90 pulse. There may be pulse imperfections. Refocusing may not be efficient. For that, there is an experiment called corpuscle sequence, which goes n number of times. This is a sequence which you are going. It is a Maeboom-Gill modification, CPMG sequence it is called. And then what we will do is we apply number of such pulses. See, the echo start decaying like this slowly, and see there is a echo here and maximum echo is here and then start decaying. It is exponential decay is there. Here at each intervals in between we are applying the 180 pulse to reverse the spins. So, number of times you start a spin to go from one axis to other axis by 180 pulse. Keep on changing, asking it to go back from this place to this fast moving to slow moving component, slow to fast, keep on interchanging by 180 pulse. In the process, inhomogeneity contribution can be drastically reduced, and there is a natural decay here that you collect, and then you can do this by curve fitting. Of course, as I told you, if still there are errors in the 180 pulse, we can use this by what is called Maeboom-Gill modification sequence, where number of echoes become more. Of course, that is the corpuscle Maeboom-Gill modification with more number of echoes, and this is how the spin echo actually in an experiment has decayed. Okay, you have measured the intensity of the peaks as a function of spin echoes. There is a reduction in the intensity due to natural defacing phenomenon. Calculate the intensities and then do the curve fitting. The intensity what you are going to measure in the xy plane could be mx or my, does not matter. You fit into this equation m naught into exponential minus t by t2. This is also exponentially decaying. So, when you do this, of course, m naught is the maximum signal before defacing, and mx by my is what is the signal after defacing. Fit it into this curve, you get what is called T2. Very easy method of measuring the T2. Okay. So, this is what I wanted to tell you. With this, we discussed a lot about relaxation phenomena, relaxation concept, processes that involved in relaxation. What do you mean by relaxation? What is the way space system gives energy to the lattice in the spin lattice relaxation? The mode of interaction, mode of energy transfer, how the heat get dispersed. Where heat is a thing we discussed. Similarly, what happened to spin lock? What happened to the spin relaxation T2? How these two differ? Lot of things we understood. And of course, this class we also understood how we can measure T1 and T2. The common experimental methodology that is adopted for the measurement of T1 is inversion recovery, which is 180 tau 90 tau sequence. Apply a 180 pulse, bring the magnetization to minus z axis. With a tau delay they start going backwards, then apply at 90 pulse and start collecting the signal and do the Fourier transformation. Measure the intensity of the signal at different values of tau, do the curve fitting for the equation mz equal to m naught into 1 minus 2 into e to the power of minus t by t1. That will give you value of t1 for different peaks per second. Same way, spin echo experiment you can do, 1 echo or 2 echo, n number of echoes gives rise to, it takes care of pulse imperfection, everything. One single echo is Corpuscle method. More number of echoes is Corpuscle-Meibum-Gill modification method. So many things are present. So many echoes are there, which takes care of inhomogeneity contribution to a magnetic field and also pulse imperfections. Finally, measure the intensity in the x-axis. This pulse sequence is reverse of the T1 measurement. There T1 is 180 tau 90. Here is now 90 tau 180 is a T2. Okay. But in this case of this, there is a echo. After 180, there is an equal amount of time is given, and then collect the signal and measure the intensity, echo amplitude, how it is decaying, naturally defacing, and fit into this curve, you measure the T2. So this is what I wanted to tell you about concept of T1 and T2, how we measure everything in this class. So we have covered a lot extensively for relaxation phenomena. This being the advanced course, in the previous course I didn't teach about relaxation. This being an advanced course, I touched a lot about these things and discuss as much as possible in a basically conceptual way. I hope you got some point. This is very useful for your research activities later. So with this I am going to stop now. We will continue with other topic later. Thank you.